Stop constructing. Stop making yourself complicated. Oh, you're the one who's not that. But that's really.
Oh, you sure? Thanks. Okay. Good evening, everybody. Thanks so much for coming out. I guess it's almost evening. Today, the Carthage Institute of Astronomy is presenting or facilitating or introducing or bringing to you the Carthage Microgravity team, which just a couple weeks ago was flying high above Texas, up and down and up and down and up and down, as I would tell my daughter, wherever she is, learning how to be astronauts. They were there actually working with Kevin Crosby on a NASA program that they'll tell you all about. And so if you had a chance to see the Kenosha News. Sorry? Professor Crosby's over here, yeah. There it is. If you had a chance to see the Kenosha News a couple weeks ago, they were featured every day for a week, which is really very exciting. So we have Kevin Lubbock, John Robinson, Steve.
Yeah, that's me.
Yeah, Matthew and Danielle Whelan. And I'm Brian Schwartz. I'm going to get out of your way. Thanks so much.
All right, well, thank you for that introduction, Dr. Schwartz. As he said, we're the Carthage Microgravity team, and my name is Stephen Mathy. And I am a junior chemistry major. This is my second year on the microgravity team, and this year I was responsible for designing the experiment, or designing the rig, I should say, that the experiment went in, and was also responsible for doing the structural analysis, verifying the safety of everything from the rig. And so, well, the rest of us will introduce ourselves here. So.
I'm Danielle Weiland. I'm a sophomore at Carthage. I am majoring in physics with a minor in computer science and math. This is my second year on the microgravity team as well, and I've been the outreach coordinator, so planning stuff like this, and then also the electrical engineer.
My name's Kevin. This is my first year on the team. I'm a junior, computer science major with minors in math, physics, and Spanish. I was in charge of the software as a software engineer, making sure that it would work and that it would be easy to use in the microgravity environment. You know, make sure people can use it while floating around.
And I'm John Robinson. I'm a junior math and physics double major. My first year on the team, and I was pretty much one of the all-around players. I did a lot with data analysis, and I was helping Danielle with the electronics, and I was also mainly in charge of the hazard analysis, so making sure that there aren't any major problems that could happen with the rig.
All right, we'll go over more about each of those different documents later in the presentation. So, all right. Next slide. So things we're going to talk about today, we're going to start off with what exactly is the NASA SEED program, and then we're going to go into our acceptance of the program, and then what we're doing in the program, the science behind what we're doing, how it works. And then we'll go through all of the hard work that we did on our way to Houston and Ellington Field, and then onto the flight days. And then with the hard work still to come in analyzing the data and doing different outreach events like this. And then we'll finish up with some questions. All right, so the first thing, what is the NASA SEED program? The NASA SEED program is put on by the Reduced Gravity Office. It's called the RGO. And it's put on through their Microgravity University program. It's a subset of that. And so SEED actually stands for Systems Engineering Educational Discovery. And it's aimed at teaching undergrad students, like undergrad teams like us, the principles behind systems engineering. And systems engineering is basically the science of breaking big problems into little individual ones. So you can have multiple people working concurrently on different aspects of the same problem. And so you can see that a little bit in how we divided up everything. All of us had our own areas that we were working on. And so what this SEED program actually is, it's a competitive program put on by NASA. And we begin the application process actually as soon as we got back to school in September. We started working out the application to submit to NASA. And in that application, we demonstrate our understanding of the systems engineering principles. And in doing so, we have to write about an example of systems engineering. And our example was the Mars rover, which is currently most of the way to Mars. It lands there in August, I think. And so then, as I said before, SEED pairs undergraduate teams with NASA researchers to work on problems that NASA has that will benefit NASA and then spaceflight in general. And this is our 5th year applying to the program and our 5th year getting accepted to the program. And just a selling point of that for us is we're one of 2 schools in the whole country who have been accepted to this program, to the SEED program, all 5 years of its existence. The other school is University of Nebraska. Right. And so, yes, we did get accepted. We found out in December, like the first week in December, we got our acceptance information, and we were all very, very happy. It was a great time for all of us, and then also kind of sad at the same time because we just realized that from December to April was now gone and occupied. But we'll go into that more later. So this was our 5th trip down to Houston, Texas. And so I'll pass it on to Kevin with what exactly are we doing?
So one problem that NASA has is that stuff in zero-G doesn't behave as you would expect. For instance, liquid sloshing around in a tank, or liquid in general, doesn't seem to hold the shape of a container like it does in 1G. And that makes measuring how much liquid is there rather difficult because things are always moving around and the techniques that we would use here on Earth don't quite work. And I'll explain a little bit more about that in a minute. We were paired up with Rudy Weirlink. He's a NASA engineer who works in Florida to continue work on a zero-G fuel gauge that we had started last year. Last year we had got about 4 data points out of from all of our time working down at NASA, and our hopes this year were to get much more than those 4 points, to get upwards of 20. That would really allow us to prove the veracity of this technique or not. So as you can see, like water tends to float, and it kind of congeals in odd shapes, almost like as if you blew a bubble here on 1G. How we measured, how we measure stuff here on 1G is we usually put something that floats in it. Like right here, we've got a green liquid, and I've got a tennis ball suspended in it. And if I would let some of the liquid out, the tennis ball would go down. If we measure where the tennis ball is, that tells us how much fluid is in there. Well, this doesn't work in zero-G because the ball doesn't float. Floating doesn't really have a meaning in zero-G, and so this ball kind of suspends itself in the liquid, just like fruit would suspend itself in Jello. In fact, we've got a video of that coming up here shortly. Current methods for bypassing this involve burning fuel, so they punch the gas, if you will, accelerate the rocket that forces all the liquid to the back of here, and then they're trying to measure something that floats. But that'd be akin to having to get your car going like 90 miles an hour on the interstate to figure out how much fuel you've got left in the tank. A, that's wasteful acceleration. B, you're burning gas to figure out how much gas you have in there, and it's relatively, it's not terribly accurate. And the additional fuel that you need to burn to figure out how much fuel you have, that's extra weight that they would need to take up into the tank, which it costs about $10,000 a pound to get something into space. Other techniques include pressurizing the tank and measuring how much the pressure changes, but that adds a whole extra amount of hardware, and for these huge fuel tanks, that's a lot of helium that they would need to ship up. More weight is the problem there. Or finally, the third option is bookkeeping. Hoping that your fuel is getting burned at a consistent rate, and you just keep track of how many seconds are going by there. Again, that's susceptible to how accurate are your readings, how well do you know how much stuff is getting burned. All right, so let's take a look at the video of this. Just a quick aside before we go to the video. This picture, and that's the background for all these slides, was taken out of the plane. And this was in the 2G, and this line right here, that's the horizon. So the plane is doing this at this point in time. That's simulating the 2G environment. And then in the 0G, it's going the other way. It's in a free fall. I thought that was kind of cool. So what we did is, you'll notice there's Velcro on these 2 tanks. What we did is we Velcroed this to the inside of our secondary that has the big metal tanks, and then we put a camera on it during a couple of the 0G parabolas. Just to watch what happens. Right now we are in the 2G session, so it's floating as you'd expect. It's just sitting there as per normal. But in a couple of seconds here, we'll have hit the top of our parabola and things will start floating. Get ready for it. Wait for it. And keep your eye on the ball. All right, so we're starting to float, and the ball just kind of sinks down to the bottom of the tank there. See, it's suspended in the middle of that liquid. And, just kind of bopping around. So if you were watching that, your fuel gauge would be going. And you'd have really no idea how much is in there. Here's a different parabola, different angle. Same thing, the fluid is kind of floating around. There's the orange ball we have right there before our cameraman got distracted. And so that's why conventional methods don't work. So we need, our NASA engineer had this idea of an alternate solution to this problem. And you may be familiar with yourself. If you've been drinking wine out of a glass and rub your finger around the top, it hums, if you will. It resonates. And if you drink a little bit more, that frequency goes up. And if you would add more wine, that frequency goes down. Our goal is to do something very similar to that. In fact, that tank right there, Steve, give it a good rap. It resonates very nicely. And we found that an empty tank resonates at about an A above middle A. So like 880 hertz if you're musically inclined. And as we add more fluid in 1G at least, that goes down to about 600 hertz or so. We can track the hertz, and it matches pretty well with the fluid, at least in 1G. Our goal was to put it up in 0G and see if we're able to track that same thing.
So, once we got our acceptance at the beginning of December, and once we'd gotten through our finals after that, once we got back to school in January, we really started buckling down and getting a lot of work done. So we had to, basically, we had an entire experiment to build in about a month and a half so that we could have time to test it. So we were spending our nights and our weekends down in the basement in a room with no windows, no natural light to speak of. Some of us went a little crazy, so we had to goof around a little bit. Yeah. But eventually we did get the experiment finished and working, and so at the beginning of April, we shipped the rig down to Houston, and we followed about a week and a half later. So.
That's a really cool picture, by the way.
Yeah, so this is actually a picture from last year. This is an astronaut, Clay Anderson. He had spent several months up at the International Space Station. And, Steve, it's you in the picture. Why don't you explain it?
Yeah, that's a picture of me getting a fist bump from Clay Anderson. Actually, last year, this is a picture from last year. Last year, I was the only guy on the team, and there were 8 people on the team. So that's me and 7 girls. So I got a fist bump from Clay Anderson for that one.
So while we were in Houston, we were working at Ellington Field, which is an Air Force base that NASA has a part of, the Coast Guard has a part of. Basically, it's just a big airport where everyone has an area. And so the first day that we got there, we spent the morning basically just going over the rules. Where are we allowed to go? Where are we not allowed to go? What are we not allowed to take pictures of because they don't know whether or not we're selling things to terrorist organizations, that sort of thing. Then after lunch, we were able to actually look at our rig for the first time in 3 weeks, which was kind of scary. Fortunately, nothing went wrong during shipping, so it was working right out of the box, which made our lives a lot easier. Then over the weekend, there were just various outings with the other teams. There were some tours of different NASA facilities. So for instance, we went and we saw the Apollo era control room. We saw the International Space Station mission control room. Just a bunch of different places like that. Then on the Monday that we were there, we had our big test readiness review, which is basically when about 24 NASA engineers come around your rig and try to find out everything that's wrong with it. And so, Steve, you want to talk about that since that was
All right,
your
yeah,
job?
I'll take that one. Yep. The TRR, it's the test readiness review. Here. And as John said, it's when 24 NASA engineers come around and try to find what's wrong with your rig. Because what they're actually concerned with at that point isn't so much the science of the rig, but is it safe? When you put the thing on the plane, are pieces going to break off of it and go flying around and hit other people, hit experiments, hit electronics in the plane, which would be really bad, and just general things like that. So what I did was I took the NASA engineers on like a walk through our rig, all the different safety things we put in place to minimize the risks that could appear. And on the bright side for us, we got through that pretty well. The engineers didn't voice any major concerns with our rig, so we were really happy that we were all set for flight.
And so then we had our flights themselves, which we actually had to condense 2 days worth of flights into 1 day. Normally we would have 1 flight per day, but due to some circumstances beyond our control, we had to have 1 flight in the morning, 1 flight in the afternoon. So Steve and Amber and Kellyanne went in the morning, and then Danielle and Professor Crosby and I were on the afternoon flight.
This is the cool part. This is what you guys can see. This is when we're all floating around, doing all the pretty fun stuff. So it's just a short video of kind of what happened while we were on our flight.
The experience of flight was just incredible. It's just you're sitting on the floor and then all of a sudden you're not. The coolest thing I've ever done in my life, for sure.
The experience of the flight was better than any roller coaster combined. It actually went by really quick. I didn't get sick at all, which was really unexpected because the most thing I was worried about was getting sick. But went through the whole flight. At the end, I got to go do spinning, which I did not plan on, but it was a lot of fun. I hope to do it again next year.
I did gymnastics for 10 years, and so I was sort of playing around a little bit with some of that stuff in 0G. I think I actually flew across somebody's rig while I was flipping, and it was just super fun.
It was just so much fun. Towards the end of the flight, I guess I could probably start feeling my inner ear coming back a little bit. Because I remember towards the end, I remember telling Amber about this too, like during the flight. Like there were times where I would have sworn I was upside down, but my eyes were very clearly telling me I wasn't, I was right side up. But my inner ear was telling me I was upside down, and it just felt weird having that conflict there, and it happened on a couple of the parabolas.
At one point I was holding a Carthage pom-pom, and it looked like an underwater sea kelp field where it's just slowly waving in the air. It wasn't keeping time or anything, but it was moving around in the 2 compartments, and it looked like water was sloshing around.
At the end of the flight, they had two other parabolas they did. One was lunar gravity, which is about 1/6 of normal gravity, and then the one that was Martian, that's 1/3 normal gravity. You still weighed something, but you weighed a lot less. And so, like, I was just jumping around during the lunar portions. It was fun, and like you'd jump up and then you'd like float there for a bit, and then you'd come back down.
When we were actually working on the rig was during 2G, and I'd have to like scoot over and pull on the different cords when we were draining. And then in 0G, Kelly had to try to write information on the clipboard in 0 gravity. So that must have been an experience.
The experiment went pretty well, probably as good as it could have with the time we're given. I think we got in every data set we needed. It looked a little bit different than it does on the ground just because of the sloshing of the fluid in 0 gravity, but we definitely got solid data.
We're going to be analyzing data, making graphs of it, figuring out how it worked, and then the important part, figuring out what that means. It's one thing to make a pretty picture, it's another thing to say, okay, because we have this peak moving here, this standard deviation in that, well, that means that we can only get 6% resolution, or well, because of this, we can get maybe even less than the 2% we've been working for. So yeah, at this point, it's just going to be analyzing for a while.
How many things did you count floating? everything, pretty much. All right, so that's what we go for. We go about 6 months out of our school year to get 15 minutes in zero gravity. It's a pretty big deal. So like we said, it was just a really cool experience, nothing that you could ever imagine. And now, what do? It's all over. It's not done though. We still have data analyzing to do, which we're currently working on. Steve will be leading that for the summer. Him and Kevin will be doing some work, trying to get the next step of this process done. So during flight, we took thousands of data sets. It was too many to count. Because like we said earlier, we were just trying to get more data from our project last year. So right now, we are creating graphs, like we said in the video, getting usable data. And what NASA expects from us now is a final report on our findings and also what we have done to get NASA's name out there. So this is one of the things, obviously, we're coming to talk to you guys. And we also did a bunch of school stuff. So this is our list of outreach that we did. So we went out into the community, we went to schools, we asked if we could talk to the students and get them involved in science, space studies, and then all the STEM fields, so science, technology, engineering, and mathematics. As you can see, it goes all the way back to November this year. We started at Jane Vernon Elementary School with a science fair. They came to us about that, and it was really cool because they do this annual science fair, and they get their entire school almost to go there. So we contacted 800 students and their parents, which is a really big deal. So hopefully we're getting our word across that space study and science is really important. Then we did some other schools, Jefferson, Carthage. We did a family fun night, which is a public event. So we'll be doing it again next year. Basically what we did is we talked this year about just Bohr and the model of the atom. But last year we actually did a Magic School Bus themed science night. So as all of us from the 90s remember, that was like the best science show that there was. But we did the episode where there was like a meteor that was going to crash into Earth, and we had to figure out how to save the planet. So we had to send astronauts out there to study asteroids and meteorites and tell the difference between comets, asteroids, meteorites. And the kids had a lot of fun, and at the end they got to become astronauts and they got to take their picture. So that was a really cool thing. We went to a middle school, and then we also, for the second year in a row, or third, got to judge a science fair for high school students. So we got to go to them and say, you know, this is something that you can look forward to in the next 2 years. There was about 600 students there that we were judging, which is a huge amount. So these are all kids who are actually interested already in sciences, technology, engineering, and math, and we're just trying to push them the next step to get them interested in NASA and see what the possibilities are in that way. And then we're here talking to you guys, best part. And we just wanted to tell you that the next event at the Kemper Center that the Carthage Institute of Astronomy is doing is going to be for the transit of Venus on June 5th. We don't have the timing yet, but don't forget about Venus. And that's the end. You guys have any questions for us?
Actually, before we do questions, first I want to thank a couple people. So first, we'll thank the Kepler Center for hosting us and giving us the facilities to do this presentation. I also want to thank Rudy Werlink. He's our NASA engineer. This is his project that we're working on, and he chose to work with our team. This is the second year we've worked with him now, so we're really thankful to Rudy. I want to thank our mentor, Dr. Kevin Crosby, who gives us all sorts of guidance on the project when we're running into the abundant roadblocks through different things. We also want to thank the Wisconsin Space Grant Consortium, which provided funding for our science. And is there anything else I'm forgetting there? Yeah. All right, there we go. Now we'll take the questions.
How did you choose the schools other than Jane Vernon?
Since I'm the outreach coordinator, I pair with Christine Pratt from the school district office of outreach. And she came to us and she said that there were some schools that were interested in what we had done last year with the outreach events. And so they came to us for all of that. So they all came to us based off of what we've done the last couple years. We're just trying to get as many people as we can understanding why NASA is important, why science is important, and we reached about 2,500 people total this year.
So you didn't have to eliminate anybody. You were able to take all the schools that put in a request.
One day we had to split ourselves up because we had two at the same time, so we did divide and conquer there. But
Yeah.
we got her done.
We keep looking for more people to come talk to, so.
How did participation in this project change you?
It's on a person-to-person basis. Let's see. Kevin?
Well, I've always loved to solve problems, and working on something like this gives me a wide variety of problems to solve, whether it's trying to figure out why we've got so much interference in our signal, how to make a connection work when we don't have the right parts, how to make the software work. The software is a little bit different than anything I've dealt with, so I had to learn a whole new language that was about as different as learning a real human language all by itself. And that's, you know, kind of reinvigorated the love I have for solving problems.
John, what did you learn from this project?
Well, for me, I'm kind of the odd one out here. These three are all in engineering. I'm a lot more theoretical side of physics. So what this did for me was, it basically gave me just a whole nother layer of appreciation for the work that goes into the experimental side. Because the theorists like to think that they can do everything that they want just by hiding in a basement with a few dozen whiteboards. But at some point you gotta go out and actually figure out, okay, does the math actually match up with what's going on in reality? And for that, you do need to be doing experiments. What something like this has done for me is it just really helps to, for a few years down the road, just to look back at this and say, okay, well, remember all those problems that you were having way back when? The experiments are bigger now, so the problems are going to be bigger. So don't get annoyed when you're not getting your answers right away.
Okay, and then, as I said before, I'm a chemistry major. Know I wanted to do something with chemistry since sophomore year in high school, but my participation in this program has sort of changed my idea of where I thought my career was going to go. So participating on the team last year, and then last summer I had the opportunity to go see the last shuttle launch in July, and just those two experiences sort of like rekindled my interest in just NASA and space exploration. And so now, instead of being chemistry, I'm leaning more towards like chemical engineering in that field. And then my ultimate goal is I want to end up working at NASA in some capacity. So.
And then for me, as I said at the beginning, I'm a physics major, but I actually came into Carthage as a chemistry major. So I took chemistry and physics classes in high school, but I couldn't let go of physics. I don't know what it was, it kept drawing me back. So as a freshman, I got accepted onto the team, and I was still taking chemistry, physics classes, and then I just realized I didn't want to stop doing physics. And I got to just working with NASA and the astronauts and engineers just really made me realize this is what I want to do for my life. So I'm actually planning on going to grad school for aerospace engineering after I graduate from Carthage. Thank you. Anyone else? We like talking, so.
What is that black box? Is that a microphone?
Yeah. Nothing special.
Like one.
No, this one is not. This one's a clicker.
So do you have any early conclusion you could draw, preliminary conclusion you could draw from your experiment? Did it work?
Roughly, it's looking like it approximates working. It'll take a little bit more to figure out exactly to what's resolution we can get. You know, we'll be able to tell you that you have 37.6% fuel, or do you have between 36 and 38%, or do you have about 40%? You know, just how close can we get to the actual with our data that we have?
So in short, it works. We're just trying to figure out how well it works.
And how we can make it work better, if possible.
I agree with that. Do you think you guys will all want to be on the team next year?
Yes.
Yeah.
Definitely.
You kind of can't get away from it after you start. It just keeps like sucking you back in, even though you spend, 6 months of your school year working, doing this, doing schoolwork, maybe working some more on the side, You basically don't have any time for anyone else but the job that we're doing.
And at the same time, as we said before, this is a competitive process, so that's entirely dependent on our application, which we'll be putting together in September to October again.
Is there a limit to how many people can be on the team?
There's a limit of how many people can go down to Houston, but we can have as large of a team as we want at Carthage. They just wouldn't get the experience of going to Houston with us. But we can have up to 7 people. We actually have 2 other students who are not here tonight. They had other stuff. But we had Amber Backham, who you saw on the video. She was our team lead this year. She's also graduating, so she's got some senior thesis stuff to do. And then there was Kellyanne. She's also a physics major, and she got to go down with us as well.
And last year's team lead is
Yeah, Kim Schultz is here. She was a great person to have on the team last year. She kind of reeled me in also to this.
You worked in parallel, but I'm sure you learned a little bit about teamwork too, huh?
Definitely. We had to, before we could even start our process, back in January, before we started building, we had to do a whole nother document that we didn't talk about too much, but it ended up being about 100 and, how many pages do you?
I don't know.
Like 120 pages maybe.
That was like all of the documentation combined that we wrote for this project. It was so much writing.
Yeah, but in order to get to that point, we have to lay out everything we have to do, because we couldn't do some electrical stuff or some software stuff until we had some hydraulic stuff or some tubing that was put in. So,
for instance, we couldn't put the electronics together until the base was together. We couldn't put the base together until Steve designed it and did the structural analysis of it. And I couldn't do the software until the electronics was in, and we couldn't necessarily do the whole water test until the electronics was in. So a couple of things we were waiting for each other, but other things we could work on at the same time.
It's one of the challenges.
You could grow to love each other, to hate each other. I mean, you learned a little bit about tolerance.
A little bit.
yep,
Yeah.
12 hours in a basement with pizza and bagels and no light. So
Yeah,
we love each other.
good.
Yay.
Any other questions about anything about the microgravity team? Anything you saw on the slideshow? Anything about future work we're doing? Anything?
In case you're wondering, the drugs that they give the flyers really knock them out. Amber got done with Flight 1, sat down and slept throughout the entirety of Flight 2 for like 3 hours straight, which means that I was basically the only ground crew member. So I was the only one in charge of moving, making sure that we were ready for Flight 2 after Flight 1. But those drugs were kind of powerful.
Yeah, an interesting side effect on just having to condense down into one day is that all of the flyers were drugged up on the same day. So Kevin got to deal with all of us.
All right, if that's it, thank you again for coming out and taking the time.
Thank you again.